is not too messed up. But anyway. So I've got this A right here. And when I write delta x or delta y, what I'm doing is moving away from this point. And how? In some completely random direction? Oh, I bet that's a no. Or along the tangent line, or along the curve. When I write delta x, am I going to go along the line or along the curve?
Along the curve.
Along the curve. Okay, what do you call it when you move along the line?
Dx.
Dx, okay. So out here, this is going to be a plus delta x. And of course, I need two coordinates. So here I'm talking about a and b. But look, I changed both the x coordinate and the y coordinate. So this would be b plus delta y. Okay? And along here, I'm going to call the changes d something. So this would be a plus dx, comma b plus dy. And I'm not doing anything. I'm just drawing pictures and giving notations that connect with the pictures. It's going to be kind of tougher to draw them over here because the picture's more complicated. But anyway, I'm just drawing pictures. Now, y equals f of x. That's the assumption here. And that means that every point on this thing, every point on the curve, has to have the y coordinate equal to f of the x coordinate. So when I look at this point, AB is on the graph of y equals f of x. And B is the y coordinate, and A is the x coordinate. So I have this, right? And for this point out there, A plus delta x, comma, B plus delta y, is also on y equals f of x. So what does that tell me?
On the plane.
B plus delta y equal x plus a plus delta x.
Is
F of
f of a
a
plus
plus
delta.
delta x.
There we go. So I'm just plugging this point into this equation. This is the equation of the entire curve. Okay? And when I subtract these two, then I get that delta y is f of a plus delta x minus f of a. That's the numerator in the difference quotient. And all I've done is started at some point, this fixed point AB, and just moved along the curve. And automatically, when I write down these coordinates, when delta x and delta y represent the changes in x and y along the curve, then the delta y turns out to be exactly what this is. So this derivative is actually the limit as delta x goes to 0 of delta y over delta x. Now, what's the other notation for the derivative in Cal 1? dy dx. Okay. So, what I have here then is dy dx. Now it's evaluated at x equals a. But still, it's dy over dx. A change in y and a change in x. Well, of course, and again, my picture is cluttered. Sorry about that. Let's just draw the tangent line. Well, I guess it was supposed to go, well, pretty close to the origin. All right, so here is A and B. And out here somewhere is, well, let's say AB. And this is A plus dx, B plus dy. And so the gaps here are dx and dy. And naturally dy over dx is the slope. So naturally dy over dx is the derivative of the limit of all that mess. Okay. Now let's go back to this picture. Oh, one more thing. Back to the equation of the tangent line. If I apply this point, so here's the equation of the tangent line, and what if I'm at this point? If x is a and y is b, then all I get is 0 equals who cares times 0. But if I'm at the other point, so at a plus dy, dx, b plus dy, then what I have is y, well, what I have is b plus dy minus b equals f prime of a times a plus dx minus a. So look at that, the b's cancel, the a's cancel, and I have dy equals f prime of a times dx, which is just what it should be. Because, you know, that's what it says somewhere, right there. All right. And all I'm doing is I'm moving out along the curve or moving out along the tangent line. When I move out along the curve, I get a delta y, and where is it? Here it is. This is the formula for increments right here. And by the way, that's the word, increment. An increment is a change in the value of a variable along a curve, or in 3 variables along a surface, or in 15 variables along a graph of some sort. Okay? And what's the other one called? We got increments and what are these guys called? The D things. What's the long word for them? We just don't have enough long words in math, do we? Integrals have them. What's the word for that? It's not derivative.
Differential?
It's a differential. Okay. So increments are changes in the value of a variable along a curve, or more generally a graph. And differentials are changes in the value of a variable along a tangent line or a tangent plane, or in general a linear approximation. Okay? Now let's look at the formulas for increments and differentials for functions of 2 variables. So I've got my point ABC right here. And let's just move out along the surface. Let's move right there. And you might say, wait, aren't you supposed to go along either this curve parallel to the YZ plane or this curve parallel to the XZ plane? No, I just want to make a change in the variables along on the surface. And I can go any direction I want on that surface.
And that surface isn't necessarily a plane, right?
This one, this curved one, is not necessarily a plane. The tangent plane is necessarily a plane.
Right.
Right.
I was talking about the surface.
So that the surface itself is not necessarily a plane.
It's a geodesic, right?
Not necessarily.
Oh,
So let's see, for example, suppose we have my favorite curve.
Because it defines the surface.
X squared plus y squared. My favorite surface, I guess I should say. So here's my good old paraboloid. And suppose we are looking at one of these curves that you get by going parallel to the coordinate axis. So how about if we go parallel to the YZ plane? Well, in the YZ plane, if I take this curve right there, I do get a geodesic. But if I go in front, if I go out here to like x equals 1, cut through in front of the board, I still get a parabola. But it's not a geodesic. Geodesic, what's a geodesic?
It's the shortest.
The shortest curve, okay. And so if I'm up here along this parabola somewhere, I don't want to dip way down here. The quickest way to get from there to there is sort of like go around up there. It will not be the level curve either. It'll be slightly below the level curve. But yeah, it's not necessarily a geodesic. In fact, most of the time it's not the geodesic. And again, with that same argument that I gave you a while ago about elementary function or non-elementary function, you know, the ones where it actually turns out to be a geodesic are few and far between. Anyhow, so I'm going out to this point, and I've changed the x, and I'm on the curve, not the tangent plane. I've changed x, and I've changed y, and I've changed z. So I've got ABC, and I got this point. And what's the equation here? The equation is z equals f of xy. So play the same game that I played over there. Play the same game with this point, the z coordinate, right there. The z coordinate is f of the x coordinate comma the y coordinate. And again, that's since, I'm going to call this one point P, and I'm going to call this one point Q. Since Q is on the curve of these circles, since Q is on the graph of z equals f of xy, then C plus delta Z equals f of A plus delta X, comma B plus delta Y. Okay? And since P is on that surface also, then C is f of A plus, no, just f of A comma B, right? So the coordinates of P are just ABC, and the coordinates of Q is Fred, George, and Albert, okay? These three things here. And now I'm gonna subtract. So I've got C plus delta Z minus C, that cancels. So delta Z is going to be F of A plus delta X, B plus delta Y, minus F of AB. And right there, that's a key difference between Cal 3 and Cal 1. Between Cal 3 and Cal 1 and 2. Because when I just meander away from some point on the surface, I'm probably changing both X and Y. But when we do a partial derivative, we're only changing one of them. So yeah, a while ago it wasn't X plus H and Y plus H. No, it was just, it had to be in that same, well, in this case, the X direction. And I've already been at pains to point out the ways in which partial derivatives are different from ordinary derivatives. And this gets to the heart of it right here. Now let's look at the tangent plane. And I've always found it incredibly messy to have to use the same picture for both of these arguments. I can get away with it in 2 variables. I cannot get away with it in 3 variables. So I'm going to redraw somewhere. I guess here. There's the tangent plane. Where's the surface? I don't know. But anyway, here's the tangent plane. This is the point of tangency. And here's the line parallel to y and z. And here's the line parallel to x and y. And if that looks a little bit steeper than over here, well, that must be because this has a negative slope that way. So anyway, this is the same ABC. This is the same point P. And then I come over here to some point Q, and again, it may not be it may not have the same A or B. I might change both X and Y and Z. So this is going to be point R. Q is on the surface. R is on the tangent plane. And I'm going to make it A plus dx, B plus dy, and C plus dz.
This is on the tangent plane, not the surface.
This is on the tangent plane. So I'm trying to draw straight lines as best I can. Okay? So over here, I'm just trying not to draw a straight line. Okay. So, putting this in here, R is on the t-plane. And where is it? Right here. Here's the equation of the tangent plane. So I'm going to put these coordinates in here. And let's just say it this way. I'm not going to write it all out like I did before. But look, what is a plus dx minus a?
Dx.
It's just dx. So when I do x minus a, x minus a, this x minus a is just dx.
And in this case, you're just subtracting the value of the original point
Yeah.
to find the difference between the two.
Yeah, it's like a vector.
Right.
So my vector PR, the coordinates are dx, comma, dy, comma, dz. And so that's what gets put in here. dz equals the x partial at point P times dx plus the y partial times dy. This is called the formula for differentials in more than one variable. And here we have the formula for increments in more than one variable. And look what happens when we divide. When I divide dz by dx, I get what?
F of x, or f sub
That
x,
thing,
yeah, of AB
yeah.
plus f sub y, AB, dy over dx.
In other words, this x partial derivative is not found by doing the change in z over the change in x. Not unless the change in y is 0. If the change in y is 0, then that must mean that we're going along this line here. But if we just go to some random point, it's not true. And that's why they don't write dz dx for an x partial. They just use other letters. I mean, other symbols. They use del's instead of d's. So del z, del x is f sub x ab. And that's it. In other words, I'm using dx, dy, dz to go any direction I want to. But if I'm thinking about this line right here, then the change in x is del x, the change in z is del z, and the change in y is zero. But we're staying on that line. I'm staying on this constant. So notice that the del's have different meanings depending on what my assumptions are. And again, I've shown you that these, like problem 5 and problem 8 on the first partial derivative supplement, I showed you that, oh, you turn it over and it's not the same as doing 1 over something. Del x del theta is not 1 over del theta del x. And it's all related to the same thing. Okay. And again, the formula for differentials, where did it go? It's right here. The formula for differentials basically is just taking the tangent plane equation and plugging differentials in. All right. So, what can I erase? I'm going to erase this. Well, I'm going to erase all of this. So, suppose z equals f of x, y. And let's suppose that we're not concerned with any one particular point. A while ago, A, B, C was a particular point. But I can do this anywhere. So, where was it? When I was doing ordinary derivatives, I must have erased that. But anyway, I said dy dx for ordinary derivatives, that was f prime of a. That's if I'm at a particular point. But if I'm just thinking about the whole silly curve, then dy dx is another name of the derivative, and it's f prime of x. So as long as I stay right there, dy dx stays the same. But if I just move from one tangent line to another, dy dx changes. The slope of the tangent line changes if I move the tangent line. Who moved my cheese? Right? So when I move around here, the slope changes, dy dx changes, and so it's not f prime of just one point, but it's f prime of something that's. So that's what I want to do. Instead of writing the a's, b's, and c's anymore, I'm going to write delta z equals f of something minus f of a shorter something. And this is going to have a delta x in it and a delta y. But instead of writing a and b, I'm just going to write x and y. So again, as I move from place to place on my surface, if I drag the tangent plane with me, all right, then its x slope and its y slope are going to be changing. But if I pin it down to one point, then the x slope stays constant and the y slope stays constant. All right. So anyway, more generally than what I was saying earlier, this is the formula for increments.
Formula for what?
Increments. I'll even spell it this time.
I heard you say integrals at first.
I may have. I was making lots of mistakes in Cal 2 this morning. Started making another mistake. I started saying I made lots of mistakes in Cal 3 this morning. Oh, so this is Cal. And dz is, and instead of writing f sub x at AB, that would be if I was at one tangent plane and one tangent plane only, and just moving around on it. But if I was at 5, 7, then I'd get f sub x at 5, 7. But if I want to move over here, well, maybe I'd be doing f sub x at 2, negative 13 or whatever. So anyway, I'm just going to change this to variables. I'm going to make it f of xy, f sub x of xy, and then times dx, and f sub y and xy times dy. That would be dz. It has the same structure, but now I'm just not pinning myself down to just one point. It could work for any point. And now I'm going to make one more change. I didn't write this up here because I want to change the notation again. I'm going to use the classical del notation. Del z del x. I'm not even call it del f del x. I'm going to call it del z del x dx plus del z del y dy. And there's your classic formula for differentials. And all of this was for three-dimensional space where I had one variable being a function of the other two. But maybe we got something else. And maybe we don't even have x's and y's and z's. We can have any letters we want. So let's try this. It doesn't even have to be f. Maybe it's the function g. If w equals g of t, comma, theta, comma, u. Oh, let's just go ahead and have one of my ordinary variables with it. If this is the case, then two things. Delta W equals something, and dW equals something. What's delta W gonna be? Where was my sample? Here's my sample.
Delta W is gonna equal, G of, T plus something.
Something. How about calling it delta T?
Okay, delta T, then theta plus delta theta,
We're on a roll now.
then U plus delta U, and then Y plus delta Y.
That it? Minus
G T data U Y.
all that mess. What about dW?
So del W, del T times dt, and then it's plus del theta, oh, del W by del theta times
There you go.
del theta.
Now we're on a roll.
Plus del W by del U times D, and then plus del W by del Y.
Now we're getting somewhere. So what I've done, all this stuff, the book presentation of this is a portion of section probably 12.4. Let me just make sure of that so I can refer you to the right thing. Oh, sorry, 13.4. So 13.1 was, pictures of surfaces. 13.2 was limits, which we skipped. 13.3 was, and by the way, the reason that I skipped that section, they're talking about things like the limit, this is 13.2. Doing things like the limit of f of x, y, as x and y both start doing something. X and y go to, say, 5 and 3. All right? And if f is continuous, you get f of 5, 3. But and they do limits before derivatives in calculus 1 because you need limits to define derivatives. And I use limits to define derivatives in Cal 3, but not this kind. The limits that I needed were not the ones that are in 13.2. They're just ones where x is approached.